Today's lesson is on topic 2.2. So our objectives today are looking in this unit. Our objectives are going to be focusing on treating all the objects as simply point particles. Of course, we're going to be reviewing free body diagrams, what it means to be in translational equilibrium, as well as Newton's laws of motion, and treating friction in a fairly simple model, which we'll call solid friction. In terms of applications and skills that we'll need to practice, certainly we'll need to practice our treating forces as vectors, so they have a magnitude and a direction, and we'll have to do components, working our way through free body diagrams, as well as dealing with problems and Newton's three laws. In terms of guidance, okay, they tell us how we should use and label our forces. We're going to be required to use commonly accepted names or symbols, and in particular we will be translating weight to be the force of gravity acting on a mass, or mass times g of 9.8 if we're on Earth. Okay, our free body diagrams should be scaled and will pretty much be limited to constant mass. Okay, in terms of formulas, there's a couple of things about the formulas that I want to point out. The formulas on the left are the way the formulas are listed in the data booklet. Okay, we are given F equals ma, and the force of friction is less than or equal to mu sr. Force of friction is equal to mu dr. What are those? We'll talk about them in more detail, but I don't like the F equals ma formula. Especially because it doesn't even include the net force, okay? A lot of times people think, well, an individual force is equal to mass times acceleration. It's not, it's the net force, okay? All of those forces equal result in the mass times the acceleration, okay? Or even better, okay? Because the force causes the acceleration, the formula is probably better written as the acceleration is equal to the net force divided by mass. Or as Newton puts it, the acceleration is proportional to the force and inversely proportional to the mass. Okay, so first off, what is an object? Okay, an object that we're basically going to be looking at is any single thing that always acts or moves in unison to the conditions being studied. So it moves as one single thing, an object. Okay, it doesn't matter to us that, you know, a car has a steering wheel and wheels and engines and chairs and passengers. We're just going to treat it as a car. Okay, or we don't care that this block that's sliding down has, you know, literally billions and trillions of atoms in it. Okay, and those atoms have protons and neutrons and electrons. We don't care about that. As long as they all move as one, we're going to call it a single object. Okay, because of that, we can just replace the object, for the most part, as a single point. Okay, and this single point has position and velocity and acceleration, and all the forces that we apply to this object, we're going to treat as mathematically being applied at that single point. If you choose the engineering option, this simple model that we use is going to kind of break down a little. Okay, we will at that point need to apply our forces mathematically at the point of application, or effectively at the distance from the center of mass. So first off, the first law from Newton, okay, this is the law of inertia. In words, it's basically an object at rest stays at rest, and an object in motion stays in motion in a straight line unless a net force acts on it. The end of that sentence is very important, okay? We can't just remember an object at rest stays at rest and an object in motion stays in motion. At that point, it's incomplete because you have to realize it stays in a straight line and the net force must be zero. Okay, so pay attention to that, because if the net force is zero, by Newton's second law, which we'll see, the acceleration is zero and velocity therefore is not allowed to change. Velocity both in magnitude and direction. So Newton's second law, I don't like, as I mentioned, I don't like the statement F equals ma. It oversimplifies and leaves out way too much important information. You're better off remembering it as the net force is equal to mass times acceleration, or like I said, better yet, the acceleration is the result of all these net forces acting on a mass, or A equals F net divided by m. I'm using the term F net, okay, but the net force is the vector sum of all the forces acting on an object. It's the vector sum, so I can't just take the magnitudes, add them all up, and say done. Okay, the direction of those forces matters. And if I consider that my acceleration is 0, it implies that my net force is 0. So therefore, my velocity doesn't change, and I end up with Newton's first law. Newton's third law is a little bit tricky, okay? This is the action-reaction law, or the equal and opposite reaction force law. And it's frequently stated as for every action there is an equal and opposite reaction. I like to put in the word simultaneously because reaction a lot of times implies that, well, the first one has to happen before the second one happens, okay? And it's not, sometimes people get confused with that. So I like to say that the two forces occur simultaneously. I push on you, you push on me. As long as we're touching, we are pushing on each other. Okay, so all the forces that we deal with are going to come in pairs. So just to summarize, okay, all forces, okay, it doesn't matter whether it's a contact force or a field force, okay, like gravity or electrical, all forces require two objects. The force of gravity is not this mysterious force that comes out of nowhere. Okay, the force of gravity is the force of the Earth acting on the object. The force of the string acting on the object. The force of friction acting on the object, okay? The force of friction is actually the force of the surface friction acting on the object. So it comes down to the force of object 1 on object 2 equals the force of object 2 on object 1, but in the opposite direction. Equal but opposite. Okay, so whenever you see that, okay, pay attention to what the two objects are because that will give you a hint that, oh, there's a Newton's third law action going on here that I need to pay attention to. And the primary method that we're going to use to study these forces is going to be the free body diagram, okay, where we take an object and we just replace it as a single dot. Whether that's because physicists can't draw and, you know, a dot is about as simple as it gets, or the fact that the dot represents the object's center of mass, doesn't really matter, okay? It simplifies our drawing and that's all we do. We can replace it with a single dot placed at the center of mass. Feel free to estimate the center of mass. The center of mass is where it would balance. You can simply treat it as the center of the object for our purposes. In terms of the types of forces we're going to be looking at, okay, we're going to have several forces. We're going to have the force of gravity or the weight of the object. The normal force, we have the F sub n for normal, or the IB likes to use the reaction force, okay, the reaction force of the surface on the object, because the force of the object on the surface is the primary. The reverse of that would be the reaction force. Okay, certainly we have applied forces, tension, friction we'll be looking at, and the other two field forces, the electric force and the magnetic force. And so all of these forces can be drawn on our free body diagram. If it's not one of these 7, okay, most likely you're confusing something, okay? It's almost always got to be one of these 7. So let's look at an example, okay? I have a 25 kilogram sled. It's being drawn by a rope at an angle of 37 degrees and a tension force of 100 newtons. And the friction force acting on the sled is 15 newtons. Okay, so a couple of rules when it comes to free body diagrams, okay? All of the forces start on the dot, okay? Make sure that it starts on the dot and goes away from the dot. And if at all possible, okay, pay attention to the scale, okay? Longer vectors imply a greater force. Smaller vectors, smaller force. Especially if there's a grid provided to you where you can scale them without having to break out a ruler, then definitely pay attention and draw the force vectors to scale. Okay. On your free body diagram, a couple of don'ts. Okay. Sometimes I see people draw the net force vector on the dot. Don't do that because it confuses the situation. Similarly, don't draw acceleration or velocity vectors on the dot. those three things, okay, net force, acceleration, or velocity, yes, you can draw them off to the side to remind yourself it's part of the drawing. That's perfectly fine, but don't draw them on the dot because then they look exactly like forces. And forces are vectors, so anytime we see a force at an angle, next thing you should immediately think of is, oh, what are the components? What's the horizontal component? What's the vertical component to this force? Okay, if you draw those components on your free body diagram, make it very clear that you are drawing the components. Use dotted lines for those. Label those things, okay, X component of this force, Y component of this force, or horizontal and vertical. Something to make it clear to somebody reading the problem that you know this is not not the actual force, but simply the components. And the reason we draw these free body diagrams is because all those forces that we draw effectively help us to calculate the net force and eventually acceleration. Or we can mathematically set them equal to each other and back calculate individual forces. And just like we talked about in projectiles, okay, forces are vectors. The math works whether we add them graphically or algebraically. If we add them algebraically, I can just simply treat my x-axis and my y-axis separately. Okay, I may have a completely different set of equations for each, but they are related. So, the simple free body diagram rules, these are enhancements. It's not required, but I suggest that you follow them anyway because it's a good rule. Okay, so one of the rules that one of the enhancements you can do is to draw the acceleration vector off to the side. When we get a little bit more complicated, that acceleration vector is going to be very important because that acceleration vector is frequently used to indicate what direction is the positive direction. Not always, but it's a good indicator. Sometimes it's the velocity vector. But in this case, this is the free body diagram that goes along with our problem. Okay, the first one I always draw is, the first one I always draw is the gravity vector. Okay, we pretty much always have gravity, and it's easy. The direction is always straight down. There's no thinking about it. Just look up, does the object have a mass? Yes, draw it. You can even put a number because the gravity is just m, or the weight of the object is just the mass of the object times g. If you use g of 10, it's not so bad, but otherwise use 9.8. The 10 is good for mental math. Okay. The next thing I always do is check to see, is the object on a surface? Well, yes, okay, it's a sled. Sleds always run on ground or snow or ice or something like that. So all I'm going to have a reaction force or a normal force perpendicular to the surface. Okay, so is there an applied force? Yes, it's being drawn by a rope. Oh, it's at an angle of 37 degrees. So I'll have to remember that. 37 degrees, and it has a tension force. I could even write in its value here because it gives it to me, 100 newtons. Okay, and oh, there's also a friction force. Okay, so here's my friction force. I can write in a value for that. It's equal to 15 newtons. Okay, and that's pretty much how it goes. Okay, I know my weight. Okay, it's 25 times 10, let's say. So I'm just going to call that 250 newtons. Look at how long that weight vector is, okay? It's 250 newtons. Compare that to the length of the 15 newton or even the 100 newton force, okay? It should be much longer. Is it 2.5 times longer than the tension force? It doesn't really look like it. I probably didn't do a great job of drawing them. I could have paid a little bit more attention, but I don't have a grid and I ran out of space. And if I made them truly to scale, that 15 newton would look really, really small. Okay, notice also, okay, the tension force, I pretty much drew in my right triangle for the components, okay? I could do the sine and cosine thing and find the horizontal and vertical components of this force. And depending on what the problem is going to ask of me, I'm almost certainly going to need those components. I don't need the 100 newtons so much, but I need those components. Thank you.